To begin this second part of the course, we're going to first examine the stuff that is most associated with the oceans, the water itself. So if we look here at the water molecule, sometimes colloquially it's called the Mickey Mouse molecule because of the two hydrogen atoms orienting themselves or bonding to the oxygen atom such a way that there's a polarity to it. You know it as H2O or HOH, and so it's written and you might think, well, it's symmetrical. There's a symmetry to it. But the way the bonding occurs, it's a strong covalent bond, and the hydrogen atoms are oriented closer together on one side of the molecule. Makes it very polarized, which means it is the universal solvent. This easily breaks ionic bonds. This is why something like rock salt, halite, which is sodium chloride, easily dissolves in the presence of water. So we have a planet filled with huge amounts of this universal solvent, water, and this is going to determine why our oceans are salty, why they are more than just pure H2O. So let's look at the chemistry of ocean water itself. Ocean water is not just H2O. It is 96.5% water and 3.5% other. And that varies. We'll show a picture of that, a map of that later. And we call that other its salinity. We don't measure it in percents, which is the normal way that most people think of these things. We measure it in parts per thousand. So it's the same thing. 3.5% is equal to 35 parts per thousand. If we look around the globe, and this is surface water, so this is not water at depth. So if you took a boat, a ship, and went around the globe and sampled the water and looked at what percentage, what parts per thousand of the water is water, it's going to be a huge amount, 96.5%. If you look at the other part, the salinity, what else is made up of it in the ocean, you'll find that this can vary from 35, 36, 37. Notice there's some places, the Red Sea here in Egypt, 38, 39, 40, 41. The higher this number, the saltier the water. The lower the number, the fresher the water. So up here near Vladivostok in Russia, there's a 30. So you see there's a variety across the map. There is a relationship with latitude and several things. So here we've got the surface salinity is the red line. That's the one you need to key in on this. And the zero line, the equator, is right here. And notice that there is a sort of peaks and valleys of this. The higher this goes, the more saline the water is. You might think that, well, why might this be so? Well, a couple of things. If we look at evaporation minus precipitation, basically how much fresh water there is coming out of the sky and moving towards the ocean, the tropics have lots and lots of rain. So you have lots and lots of water that is pouring down, entering the oceans, and so salinity is low here. As you go farther up north, notice, or south, when you reach the areas of the 30s, notice about 30 degrees north latitude, 30 degrees south latitude, the surface salinity is at its highest. We'll learn later here that there's a good reason for that. It has to do with atmospheric circulation. The ocean, the air, the atmosphere in these areas is very, very dry, which means that any fresh water or water that happens to be there evaporates, leaving behind the salts. So the 30s are salty. Go farther north or farther south than that, and again, you get this increase of fresh water and therefore a decrease in salinity. So you get this sort of double camel hump effect. Here's the same thing shown larger, just so you can see it and understand it this way. Well, what are these dissolved ions, these dissolved salts? There's the big six. You need to know them. chlorine, sodium, sulfate, SO4, magnesium, calcium, potassium, and they're the big six. But really, there's the big two. Sodium and chlorine make up 86% of all of those salts. 86%. Sodium and chlorine. That's salt. So the salt that you put on food to add some flavor to it is NaCl, sodium bonded with chlorine. In the ocean, it's also dominant, most of it. Everything else, all the other elements, and there's as many elements as there are, they're present in the ocean, but only in very, very, very small amounts. This diagram is to give you an idea of how this might appear if we were to sample salinities not just at the surface, but at depth. And so this is the bottom of the Atlantic Ocean. Here, the surface is up here, so a boat would travel sort of from east to west this way, so from Europe over to North America. Here, the mid-ocean ridge in the central part of the ocean basin, the surface has those patterns that we talked about before, but salinity also varies with depth for various reasons. Where do these salts come from? Well, there's the 6 salts that are present in the oceans. Again, chlorine, sodium, sulfate, magnesium, calcium, potassium. All of those salts come from the land. So here's a picture of the land, it's chemically weathered, this is water. The water in fresh water is not pure water as well. It contains dissolved rock, remember chemical weathering, from all of this that it's running over, and this ultimately flows to the oceans. If we look at the dissolved ions in our rivers, they are sort of the same, but sort of different. Notice there's also chlorine and sodium, but there is this thing, HCO3, that we call the bicarbonate molecule. There's calcium again, there's SiO2, and then there's sulfate. So a different big 6, and then chlorine and sodium are only 12%. This is why fresh water is fresh, it's not salty, and oceans taste very salty. Well, if the oceans are giving us this saltiness, but they're not that saltiness themselves, why is the difference? What is the difference? And here's the difference. All of the easily removed ions, sodium and chlorine, were removed billions of years ago. Today, we've had 4+ billion years of weathering of the surface of the Earth, and we're removing those less soluble salts, like the bicarbonate molecule, like silica, SiO2. The first oceans were fresher, and they got saltier and saltier till about 1.5 billion, we estimate, and since that time, they've been constant. Now, we do add salt today. Somebody actually tried to calculate the total amount of ocean salt, and look at this huge number. 5 times 10 to the 27th grams gets us to about that 35 parts per thousand for the ocean. The rivers add this amount, 0.00005 parts per thousand each year. If you multiply that times the 3.5 billion years or so that we think we've had oceans, we should have much, much, much saltier oceans. If you just do the math that way, what that means is that salt must also be subtracted or removed from the oceans today. So what is that? Several things. First of all, sea spray. When you go to the ocean, you're driving to the ocean and you smell it before you actually see it. That is, the crashing of these waves, the smell of the ocean is billowing through the air, particles that are so small they are literally flying out of the ocean and going onto the land. Sea spray. Evaporation, precipitation, removal that way. So if you take salt, go back to this one. If you have places where salt water is panned off from the ocean and the water is allowed to evaporate, you deposit big bodies of rock salt. This is how we mine a lot of our salt on planet Earth, and that takes it out of the oceans. Also, skeleton building. All those creatures that live in the ocean build their skeletons out of different ions, and that takes it out. But all of that, modeling it, is still not enough. We need another process, and that process is adsorption. So the bottom of the ocean, oceanic crust, but then that oceanic crust is covered by all those different sediments that we talked about last time, especially a bunch of clays in muds. And clay molecules, that's what this little blue broom-like thing is supposed to represent in this cartoon. They have a stickiness to them. They're not really sticky, but they aid in bonding. And so loose molecules floating in the water, like these potassium, these green ions, and these sodium ions, these blue balls, will stick to these clays. So they stick to the bottom. And then, as we know, there are plate tectonic boundaries called convergent boundaries, as shown here. You should remember this slide from last time, where huge chunks of lithosphere, oceanic crust, and mantle are subducted. They go down. So, salts stick to the bottom. The bottom, along with all the rest of the plate, gets flushed under, and that's the main removal mechanism. This leads us to this whole notion of residence time. We can talk about residence time, how long a substance remains in a system. And we measure this in geological terms in millions of years. And we have conservative constituents. These are things that once they are in the ocean, they are there for long periods of time. Then we have non-conservative constituents, and these are there for just short times, meaning they get into the ocean and then they are quickly removed by one of those processes I just talked about, mostly the adsorption one. And so aluminum has a residence time of about 600 years. That's very, very fast. If we look at residence time, so there's different calculations here. Notice chlorine, 79 million years before it's removed. Sodium, 260 million years. There's the explanation right there. Compare it to the rest of the big six. They are still in the ocean for millions of years, but much shorter lengths of time than sodium and chlorine. They remain, so they are there longer. Here's a later calculation of essentially the same thing. Sodium and chlorine, again, greatly dwarf, even more so from this estimate, the rest of these. This explains why there's so much chlorine and sodium in the oceans. There is another concept that you need to understand, a couple of them. First of all, the oceans are so thoroughly mixed that they have a mixing time of about 1,000 years. What that means is that if stuff gets in the ocean, it literally is stirred to the point where the oceans stay nicely mixed, and it happens very rapidly, this term of 1,000 years. The picture you're looking at here is a heat representation of the Gulf Stream, so it's an ocean current that originates here in the Gulf of Mexico, skirts between Cuba and Florida, and then goes across the ocean basin to Europe. And you can see by the color pattern shown by the heat that there are all these eddies and swirling and stirred places where the ocean is getting mixed. What this means is that if you look at the percentage of sodium versus the percentage of chlorine versus the percentage of silica versus the percentage of whatever, it essentially remains constant regardless of any salinity changes. How do we measure salinity? Well, You can measure both of them, sodium and chlorine, but sodium, because of that constant proportions thing, is always 1.80655 times more abundant than chlorine. Turns out chlorine mechanically is much easier to measure than sodium. So when we're measuring salinity, we typically are measuring the chlorine. All right, we'll get back to salinity in a little bit. I want to talk about another aspect of ocean water, seawater, and that is the dissolved gases within the ocean. If you look at the upper line here, the upper row, and look at this, it says the percentage in the atmosphere. And there are the major components of our atmosphere, what we're breathing today. A lot of people think that, it's oxygen. The atmospheres are oxygen. Well, that's the one that's important for our life, but it's only 21% of the atmosphere. Most of the atmosphere is free nitrogen, N2. And then we have this vanishingly small amount of carbon dioxide, less than 0.01%. In fact, it's 0.03%. The oceans have a different ratio as well. There are gases dissolved in the oceans, and notice there is more oxygen in the surface of the oceans than we are breathing. Less free nitrogen, and then far more CO2. If we consider the oceans as a whole, these things are going to change with depth to the point that the percentage of nitrogen in the oceans as a whole is 11%. The percentage of oxygen here is the smallest number, 6, and the percentage of gases in the ocean for CO2 is the largest at 83%. So the oceans are a different baby than the atmosphere, and it varies by depth and location around the globe. We can talk about the saturation value of a gas, and that is the amount of gas that can be held without causing that solution to gain or lose the gas. And this is going to depend on several things. The big ones, temperature, salinity, pressure. We'll talk about those next time. But let's look at two of these gases, oxygen and carbon dioxide. And these diagrams, at this diagram, the top is the surface of the water. If you look at the y-axis here, this is ocean depth in meters, 200 meters, 400 meters, 600, 800,000. So the great depths of the ocean. The measurement across the top, the x-axis, is oxygen, so O2 in milliliters per liter. Don't worry about the units, just realize that the higher the number, the greater the amount. Notice that at the surface of the oceans, the blue line, which is oxygen, is higher than the dashed red line, which is carbon dioxide. So this goes back to this right here. Near the surface of the ocean, there's more oxygen than there is carbon dioxide. Well, that's going to change. And as you go down in depth, there's a point, a little bit around 100 meters or so, where the amount of oxygen and carbon dioxide basically flip-flop, and we get more and more and more carbon dioxide with depth, and we get less and less and less oxygen with depth. Why would that be? The primary answer is photosynthesis. You know that plants ingest CO2, and then they create or release free oxygen. The shallow water, this area shallower than 100 meters depth, is where sunlight can penetrate and plants can grow. So they are photosynthesizing here, and they have high amounts of oxygen. Below this line, plants can't live. And so the amount of oxygen is extremely, extremely low. Notice it doesn't go, it's not a perfect curve going down. At some point at depth, you have an increase in oxygen again. And this has to do with oxygen, cold, oxygen-rich water sinking just because of the temperature difference. So there's this change. This diagram will definitely appear on the next exam. And, I ask different questions relating to the trends of oxygen and carbon dioxide with depth and why this may be so.